Hi, and welcome to the second video in a series about topology. In the first video, we looked at some basic set theory, the naive set theory definition of a set being a collection of elements. We looked at some operations between sets, such as union, intersection, and difference, and some longer laws, such as the distribution laws and the De Morgan's laws, for stringing together longer statements with sets, longer operations. We looked at the Cartesian product of two sets, and in fact, this can be done for arbitrarily many. And we looked at arbitrary unions and intersections of sets, so creating new sets from existing ones. In this video, we will explore another concept that is not only fundamental to topology, but fundamental to more or less all of mathematics. That's the concept of a function. And a function is hopefully one that you are already familiar with, at least have heard of or dealt with in some context or another, maybe not necessarily in the way that we're going to define it here, but we hope that it'll make sense why this is being defined in this way. So the way that we're going to build up the definition of a function is actually using the set theory definitions from the previous part. And we're going to start with this auxiliary definition, where we define a rule of assignment, which is a subset R, lowercase r, of the Cartesian product of two sets C and D. So it consists of some amount of ordered pairs with first element in the set C and second element in the set D. And it satisfies the condition that, as a whole set, such that every element of C appears as the first coordinate of at most one ordered pair belonging to R. Now, if this is a bit wordy of a definition, we can write this out in this logical implication. So this condition for defining whether something is a rule of assignment, whether some subset of a Cartesian product qualifies as one or not. So if we want each element of C to appear as the first coordinate of at most one ordered pair, if we have two ordered pairs, and then of course by induction more than two, with the first coordinate of this little c here, this element in big C, and if we have these second elements as D and D prime respectively, where they're not necessarily equal to one another, then it is a rule of assignment if and only if this at most one condition is satisfied. That is, if D equals D prime and they are at the same point. That is, if to each value of C, there is exactly one corresponding value of D. And this is familiar, hopefully, because it can be thought of as the well-definedness of what will be a function. A rule of assignment is itself well-defined in a certain way with respect to its first coordinate to its second. And we can represent this in a graphical manner in a way that actually recalls something called the vertical line test to test whether something is a function or not, testing the well-defined nature of, let's say, this curve of points here on where we write the c-axis here and the d-axis as the vertical one in convention with the coordinate pair, first being horizontal, second being vertical, just like the xy plane. And if we take 2 points here with the same c coordinate, this is, let's say, CD and then CD prime. This is not a rule of assignment, as you can see here, because this maps to two different values in D, so D and D prime. So this is not a rule of assignment. And you can think of a rule of assignment being something that passes the sort of general vertical line test if you map these sets as follows. Now we want to look at some other things that we can define using a rule of assignment. And these are very important definitions as well. So given a rule of assignment R, which I'll just abbreviate as ROA going forwards, we define these two sets, and two because it's based on more or less the coordinates in each pair. So we have the domain of a rule, which is the set of all C such that there exists some D in this set D, such that this point is in R, let's say. And likewise, the image is the set of all points D, such that there exists some little c in C, and then we have CD in R. So really this corresponds to all of the elements in the first coordinate and all of the elements with the second coordinate respectively for domain and image. And to specify a rule of assignment is actually equivalent to specifying its domain and its image and vice versa. If you specify the domain and image of a rule of assignment, then one can specify the rule itself given the domain and image. Now we're ready to actually define the function itself. So our definition here is, again, slightly long-winded, but hopefully it'll make sense. A function which we'll write by f, which is conventional, is a rule of assignment. So first of all, it is a rule of assignment as we defined previously, along with a set, which we'll write b, uppercase B, that contains the image set of R. So it contains all of these values of D that R reaches, so to speak, R actually hits. So we write the domain set, let's say by this big A here. If we write the domain A of this rule of assignment, we can also refer to it as the domain of the function itself, which is unambiguous. Likewise, if we have this image set, which is image of R, we can refer to it as the image, or the image set of it, or the image of the function itself. So domain and image of the function. Now this container set B has another name, and there's some ambiguity, and there's some texts which actually use image and range differently, but we'll say image is all the points that F maps into, and the set here B that contains the image set is the range. It's defined as the range. So f is a function with domain A and range B. Then we can write it as follows: f has domain A, and this arrow denotes the direction which things are being mapped into from A to B. Okay. And here's some more notation, hopefully familiar. If now f is defined this way with domain A and with range B. And if we take an element here, we want to write f of A to denote where the function takes it, which is the unique element by the well-definedness of the rule of assignment underlying the function, the unique element of the set B that we say this rule of f, rule for f assigns to A. So A gets taken to f of A. Let's take an example of how to take this rule of assignment definition with containment range set, and how do we translate it into this notation here, or something more familiar, easier to work with. We can say, let f be the function with this rule that maps like this. It takes x, and it has second coordinate x cubed plus 1, where x lies in the real numbers. So this x here lies in the real numbers, which means that its domain is R, and we specify that its range is R. So already we know that f takes the form R, and then we write an arrow, and then it also maps into the real numbers. So we specify the domain and range here, and we also specify the rule of assignment, which is given by this pair. And we can just write now, let f from R to R be the function such that f of x equals x cubed plus 1. All right, so that is function definition. Now we define something that we can do with functions given a domain. And we have this now, we have this domain set A, and we can take a subset of it, which is, let's say, A naught. And if we restrict, we say this is the restriction of f to A naught, then we only consider values that f deals with in A naught. So we sort of disregard the values that are in A but not in A naught, and we sort of make the domain smaller in that regard by taking a subset of it. So the function then mapping A naught into B is given by the rule A here, and then f of A, just like it would be prior, for all A in A naught, the subset. And it's written with this notation here. So f with this bar and then a subscript A naught to denote that it's being restricted. Okay, here's an example about how this restriction operator might look on a function, and how if we have a similar rule of assignment, we can sometimes get different looking functions just based on restricted domain or restricted image range, sorry. So let R denote the real numbers as we've been using, and we have this little notation r bar plus, which denotes the non-negative real numbers, so including 0. And we'd like to consider 4 functions here. So we have f, g, h, and k. So f, g, h, and k, as you can see here, all have the same rule of assignment, which one could write as the ordered pair x comma x squared, for example. But we've sort of messed around in all possible ways with the domain and range of each one. So for f, it maps from r to r. For g, we restrict the domain to non-negative reals. For h, we restrict the range to, so it maps into non-negative real numbers only. And then for k, both its domain and range are restricted. And by restricting domain and range, one can think of sort of in a coordinate plane, as we'll see in a moment, like sectioning off where the function is regarded, or where we can look at the function, so we can find like segments of each axis and then how the function maps based on that. Here are 4 diagrams now which correspond here. So we have f, which is from r to r, so we have the real line here times the real line here, and so we have this function which looks like this, because all real numbers are allowed in domain and range. Now g, we have as inputs, we're only allowed to put non-negative real numbers in, so that is 0, and we start going to the right from here. But the range is fine because the range is all real numbers, so we just still have this for all the values that it can output. However, now we've restricted the domain, so this left branch of the parabola that would appear in f is not present in g because the function is only taking non-negative real numbers as inputs. So we have this graph here. H, however, is going to look similar to f, despite the fact that it has different range. So its range is the non-negative reals. However, this is not any different from f, because f itself would map into non-negative reals, right? You can't plug something into f of x equals x squared on the real numbers and get something that is a negative real number. So in this case, you just get this, even though, as you can see now, this restriction of the image allows nothing to be mapped into anything below the x-axis. And finally, for k, k happens to look like g, and this is because, again, keeping in mind this restriction on the mapping, the rule of assignment itself, x to x squared, this is sort of off limits, but also we're sectioning off things to the first quadrant, or mapping non-negative reals into non-negative reals. Hence, it is this right-hand branch of the parabola, because you plug in a non-negative real, and this is what it gets assigned to. So those were, this is a useful example to look at, and I will start writing here. Sorry about that. Let's look at a definition for how to combine new functions from old ones, and it's an important concept. Once we're given certain objects, we'd like to know how to make new objects from old ones, which is something we adopted in the previous chapter on set theory, how to make new sets from old. So let's say given functions, f from a to b, and let's say g from b to c. We define the composite, and this is maybe also familiar. Define the composite function g composition f here, g composed f, g composition f maps from, now we take a to c, so we're taking first f and then we're taking g. Composition is read right to left. And it's defined by this rule, this rule here. G of f, just reading that left to right, g of f of a is, as expected, also just evaluated at g of f of a. So first we're evaluating a at f, where it takes it, and then that is going to lie in b. Then we have something in b, so g takes something that f is mapped into, takes that, and it maps into c. So this resulting thing is going to be in c. And there's a nice image that one can make here. So let's draw like circles maybe. very useful. Okay, that's not much of a circle. That's like a ellipse. Maybe 3 circles that denote the sets A, B, and C. You know, it's fine if we have these ellipses. It shows that not all sets are like same shape or something like that. So we have A, B, and C. And let's take this point A here, which f of A, maybe let's write f here. F of A equals, let's say B, because B is a point in B, so just we can define it like that. And then it gets carried by this function g. And where do I write this? So g of b, and this is, actually, let me just write like equals g of f of a, right? So it's sort of like this this progressive carrying something into a certain image set. And so let's just write this by c, since that's consistent with a, b here. Okay, so this is composition of functions, and let's just look at a quick example. Example here. Composite of both, let's say, from domain and range real numbers. So these two functions f and g. So g of x, let's say, is, sorry, let's start with f of x. 3x squared plus 2, and g of x, which equals 5x, right? So now we want to take maybe this composition g of f, which is going to equal now, sorry, let's do g of f of x, which equals g of f of x, which equals, as we have f of x here, we just plug in now g of 3x squared plus 2, and that equals 5 times this, so just 15x squared plus 10. That's just a quick example. And let's do this the other way to show that composition is not taking, so let's say f of g is not the same as g of f, and there's no reason why it should be, but let's just work it out to be sure. So f of g of x, f of g of x, and this equals f of 5x. And what do we have here? So 3x squared plus 2, so 3 times 5x squared plus 2, and what's this going to be? 75x squared plus 2. Okay, great. So this is definitely not equal to that. Let's look at now an extremely important set of definitions regarding the behavior of a function. So definitions. A function is injective if for all a prime, let's say in A, such that A is not equal to A prime, f of A is not equal to f of A prime. So basically what this is saying is that distinct elements have distinct images. So if you take this these 2 points and you take this, then they're going to be not equal to one another under f. So this is injective, and it's sometimes also called one-to-one, but we'll use injective, and it's sort of its dual surjective. If for all b in B, actually let's say specify, because it is not good to just define this and then not specify functions, domain, and range. That's a cardinal sin. So surjective if for all b in B there exists an A in A such that f of A equals b. So that is if a function's image set is its range, or rather, yeah. So if every value in B gets mapped, gets hit by F. So F reaches everything in B is surjective. And if F is both injective and surjective, both injective and surjective. And a bijection is like a correspondence. For everything in the set A, you can find a corresponding B, and vice versa. So you can line up the elements, you can match them pairwise from the domain and the range, and they will be in a perfect one-to-one correspondence with one another. So let's see. So injectivity of F, let's make a note here, depends only on the rule for F. So it depends on this rule of assignment, which let's scroll up, because it depends on how this rule of assignment acts in terms of mapping, let's say from C and D here in our first example, how it maps C to D. So these distinct points being mapped to distinct images is solely a function, no pun intended, of the rule of assignment. However, surjectivity depends only, surjectivity depends on the range of F, because it actually deals directly with these points now in the range set, because it has to do with those points being mapped back, while injectivity does not depend on the range set. It only depends on the rule of assignment. And it's a good exercise to check that composing now, as we just looked at, composing two injective functions is itself injective. Composing two surjective functions is surjective. And hence, if you compose two functions that are both injective and surjective, given those two postulates that I just mentioned, then the composition of bijective functions is itself a bijection. So let's see. Now, definition, if F is bijective, F is bijective, there exists, actually, let me just write this out. I shouldn't be using this. There exists notation in a definition. There exists a function, a corresponding function, F inverse from B to A. And this inverse is going to be a bijection as well, as we will see. So letting, if F of A equals B, sorry about that. If F of A equals B, then F inverse of B is equal to A. So this is a bijection because it's defined on all these points B, because we know it maps back to A. Similarly, F of A equals B. So it's just like reversing, and it's the inverse of F. Okay. So let's see now, given an element little b, this little b here in the set B, we can break apart the supposition that F is bijective into its injective and surjective components. So looking at surjectivity first, if we are given this B here, then there exists an element here, A, that it maps back into by the definition of surjectivity. So if this function F is surjective, then we can conclude this here. So F inverse of B, there is some A, there exists some A. And the fact that F is injective is going to be the fact that this inverse image here is actually unique, right? Because if it weren't, then it wouldn't be injective, because distinct points would map to distinct images under an injective function. Hence, this gives the uniqueness. And so this kind of this double approach of existence and uniqueness is an important concept to show that like a quantity or like an object exists and it is unique, which depends respectively on the surjectivity and injectivity. So if f is bijective, then f inverse is also bijective by what we've just said. Okay, so here is here's an important lemma, or a helping theorem. So let f be a function, and I'll just say it like let f from a to b. So if there are functions g and h defined as follows. So g from b to a, and then h from b to a, sorry. Such that g of f of a equals a for all a in this set here, this domain set for f, and f of h of b is equal to b for all lowercase b in b, then f is bijective, and not only is f bijective, g is in fact equal to h, which is in fact equal to f inverse. And just using those previous definitions, this is a really good exercise to try, so I will leave it to you to try and show this. Okay. Now let's look at some definitions based on this idea of image and how it goes now with subsets, how it interacts with sets, and instead of taking inverse images of points, we can take inverse images of, sorry, I shouldn't have used that word, inverse image yet, but how we can map points back as well as entire sets of points back. So now let's do this definition. Let f from a to b, and if a naught is a subset of a, then f of a naught is the image of the set a naught under f. And this is similar to how we defined image generally earlier, but now we're just taking images of whole sets instead of points one by one. So we're collating them into sets, and we're letting f map that whole set point-wise, and we're calling this the image of the set a naught under f. And we can write this out symbolically. F a naught equals the set of all b, such that there exists an a naught, such that b equals f of a. Okay, so that's the symbolic way of looking at it. Then if there's a counter definition, so if b naught is a subset of b, then f inverse of b naught is that inverse image that I was saying, is the inverse image of b naught under f. And once again, doing this symbolically, is the set, oh, sorry, I have to specify, f inverse of b naught a, and then f of a is contained in b naught, right? So that's this this inverse image or pre-image set. Okay, so I think we will leave off this chapter here, where we've defined functions, some ways to make new functions out of old ones via composition, restriction, We've looked at injective, surjective, and bijective functions. We've looked at images and inverse images of sets and how functions can map and map back subsets of sets. So we will see you in the next video, and there we will talk about the idea of a relation, which is sort of a more general concept of a function, but an important one as well, which you'll use. So thank you for watching, and we will see you next time.